Welcome dear students. I am V. Ragaswamy. Today I am going to explain you about the isomerism of the chemical complex compounds. So what is isomerism? So the compounds which are having same chemical composition and same chemical formula, but they differ in the physical properties and chemical properties are called as the isomers. And the phenomenon is called as the isomerism. So you can see the difference in the structures even in their solution state. So therefore we need to study the difference in the properties of these structures. Okay, now I'm going to share my slide. I'm going to explain you the isomerism and their classification in the complex compounds. So as I've explained you, the molecules with same chemical formula but differ with the molecular structure are called as the isomers. This phenomenon is known as isomerism. So basically the isomers of the complexes are classified into the structural isomers and you are having the stereoisomerism. The classification, it was proposed by Werner for different types of isomers of the complexes. Now we'll go further. See, basically it is divided into two types, the isomers, the structural isomerism, stereoisomerism. Molecules with same chemical formula with different molecular structure is nothing but isomerism, isomers, and the phenomenon is called as isomerism. So basically it is divided into two types, structural isomerism and stereoisomerism. So structural isomerism, again it is divided into 5 types. So let me see what are the different types, basic types of the structural isomers. So the isomerism which differ in the type of the chemical cleavage and distribution of the ligands within and outside the coordination sphere or within the coordination sphere is called as a structural isomerism. Isomerism, that is due to the isomerism arises due to difference in the type of chemical cleavage and distribution of ligands within and outside of the coordination sphere is nothing but structural isomerism. This structural isomerism, it is classified basically into 5 types. So still further classification, if you see, you're having 6 types. So generally we come across ionization, hydration, linkage, coordination, and polymerization. But in detail, if you see, you are having 6 types: ionization isomerism, hydration isomerism, linkage isomerism, coordination isomerism, coordination position isomerism, and polymerization isomerism. Now let us have a look onto the each isomerism with their examples. Now we'll see what is ionization isomerism. The compounds, this type of isomerism is shown by those compounds. It is shown by those compounds which have same composition but liberates different ions in different solutions. So they differ in the solutions. The compounds, this type of isomerism shown by those compounds which have same composition but liberates different ions in the solution. Now, in these isomers, the position of the groups within and outside the coordination sphere differs. In this isomers, the position of groups within and outside the coordination sphere will differ. So once if you say I'm giving you the examples, see here, you're having a pentamino, sulfato, cobalt, bromide complex. You're having here. And the other one is here, pentamino, bromo, cobalt, sulfate complex. These two are the ionization isomerism. Ionization isomers. So once if you put them in the water, on ionization, you'll be getting different ions. So in this complex ion here, the square brackets one, pentamino sulfate cobalt complex ion and the bromide ion is released in the solution. And coming to this one here, the pentamino bromo cobalt complex complex ion plus sulfate ion is released. Here a bromide ion is released, whereas here the sulfate ion is released. On putting in the solution, there is ionization difference. The complex will give you two types. One is the whole, this is within the sphere you'll be getting one ion, and outside the sphere you'll be getting one ion. Here it is pentamine, cobalt, sulfate ion is one and bromide ion is the other one. And going to this complex, here you'll be getting the square brackets one as one ion and the outside the square brackets you'll be getting as the other ion. So pentamine, cobalt, pentamine, bromo, cobalt, complex ion as one ion and the sulfate is the other ion. Both of them are having the same molecular formula, but on putting in the solution, they give you different ions. So they give you different ions. This type of isomerism is called as a ionization isomerism. Similarly, you go for the second example, that is tetramine dichloro platinum bromide complex and tetramine dibromo platinum chloride complex you see. Here it is dichloro you are having, it is here dibromo. Outside the sphere you are having two bromines, here outside the sphere you are having two chlorines. On ionize, the molecular formula is same. On ionization, you will be getting within the sphere this whole complex, that is tetramine dichloroplatinum complex, and two bromine ions are released when put in the solution. And coming to this solution and coming to this complex, when you put it in the solution, you will be getting tetramine dibromo platinum complex as one ion and the two chlorides as the second ion. So therefore on ionization you're having a difference between the ions outside the sphere. Here two bromine ions will be released, here two chloride ions will be released. Bromide ions and the chloride ions. So this is the ionization. Formula is same. On ionization, the liberated ions in the solution are different. This is called ionization isomerism. Now we'll see the second type, structural isomerism. One type of isomerism is ionization isomerism. And now let us go for the second isomerism, that is hydration isomerism. Hydration isomerism, isomers you are having, isomers having the same molecular formula but differ in the number of aqua molecules. They differ in the number of the aqua molecules attached to the central metal atom and in the coordinate sphere is nothing but hydration isomerism. Once again I'm repeating, isomers having same formula but differ in the number of water molecules attached to the central metal atom in the coordination sphere. See, now we'll see here hexa aqua chromium chloride complex, penta aqua chloro chromium chloride complex. Next, tetra aqua dichloro chromium chloride complex you see. Here all the three are having the same molecular formula, but here within the sphere you are having 6 water molecules. Here total number of water molecules, aqua molecules are the same, but here 5 are within the sphere, 1 is outside. And coming here in this one, 4 aqua molecules are within the coordination sphere and 2 are outside the sphere. So the formula is the same, but they differ in the aqua molecules. This type of isomerism is called as the hydration isomerism. Now we'll go for the linkage isomerism. So linkage isomerism, this type of isomerism arises due to presence of ambidentate, presence of ambidentate ligands. What is an ambidentate ligand? Ligand which have two different donor atoms. It is arising from the ambidentate ligand, the ligand which possesses more than one donor atom. It is having here the donor atoms which have two different donor atoms in the same ligand. The same ligand, but the donor atom will be the same. Okay, it is nothing. The best example is nitrite ion. You can take nitrite ion. The nitrite ion NO2 minus, which can attack either by the nitrogen and acts as a nitroligand. Again, the bond NO2, that is nothing but bond NO2. Through one more oxygen, it acts as a nitritoligand, ONO. Okay, ONO. So here you can see here pentamine, nitro, cobalt complex ion is there. Okay, nitro, pentamine, cobalt complex ion will take. Here the bonding of this nitro group is towards the nitrogen to the central metal atom cobalt. And coming to this complex, the same molecular formula is same for both of the ions. Both of the molecules, you're having both the complexes, you're having the same formula. But here the donor site is through nitrogen to the central metal atom. Now coming to this complex, the ligand donor site is oxygen towards the cobalt complex. Okay, so O is bonded to the cobalt. Here N is bonded to the cobalt central metal atom. So this is nitropentamine cobalt 3 ion complex. This is nitrito pentamine cobalt 3 ion. This is nitro group, this is nitrito group. Okay, the donor sites are different. The ligand, you are having the formula is same, NO2, nitroligand. Here also it is NO2, but this is nitrito ligand. Here the donor site is N to the central metal atom. Here the donor site is oxygen towards the central metal atom. Okay, the linkage is different. The linkage of the ligand towards the central metal atom is different. So you can call it as ambidentate ligand. It is having two donor sites. Depending on the donor sites, you are naming this ligand. Now we'll see the fourth type of isomerism in structural isomerism, that is coordination isomerism. Coordination isomerism, it is shown by the complexes containing both cations and anionic complexes. I'm repeating once again, coordination isomerism. This type of isomerism shown by those complexes which contain both cationic and anionic complexes, and it results from the interchange of the ligands. It results from the interchange of the ligands between the two complex ions of the same complex. Example, we'll take here one more complex. This is here. Here you're having, this is a type of complex and this is one complex. Here two complexing ions are there. Here also two complexing ions. Okay, hexamine cobalt complex with hexacyanochromium complex. Now the other one is chromium with the hexamine. Here hexacyano with the cobalt. So what you are noticing is here the isomerism, it contains both the cationic and anionic complex. This is the cationic complex and the anionic complex. Cationic complex and the anionic complexes. This is cationic complex, anionic complex, cationic complex, anionic complex. But the central metal ion is getting exchanged here. Here it results formation of interchanging of the ions between the two complexes. So the here ammonia is attached to the central cobalt ion. Here cyanide group is attached to the central chromium ion. And now coming to this complex, you can see ammonia, this ammonia molecule, it is attached to the chromium. Here ammonia molecule is attached to the cobalt. Here the same ammonia molecule is attached to the chromium. Okay, the attachment to the ion is different. Metal ion is different. And in this complex, see, this is whole is a complex. In this complex, you're having cationic complex and anionic complex. Here you're having the cationic complex and the anionic complex. This ammonia is attached to the chromium and the cyanide group is attached to the cobalt. Okay, so the central metal ion is different. Here ammonia is attached to the cobalt and cyanide group is attached to the chromium. Again here ammonia, it is attached to the chromium and the cyanide group is attached to the cobalt. There is a slight exchange of the attachment of the ligand to the central metal atom. Okay, so this is the coordination is different here. The coordination of the ligand to the central metal ion is different. So you call it as a coordination isomerism. Now coming to the second example. Here also the same. Tris oxalatochromium and hexaimine cobalt. This one. This is a cationic complex. This is the anionic complex. This whole is a complex. And this one also, it's a cationic and anionic complex. In the square brackets, one is a cation, the square brackets is the anion. Here also the same. Here, the ammonia molecules are attached to the cobalt. The same ammonia molecules are attached to the chromium. Here, oxalato molecules are attached to the chromium. Here, the oxalato ligands are attached to the cobalt. So the linkage is different. The linkage of the ligand to the central metal ion and the coordination sphere is different, but the formula is the same. Okay, so all these we are able to observe even in the solution state. So this type of isomers are called as a coordination isomers. Now let us go for the fifth type of structural isomerism. The fifth type of structural isomerism, it is coordination position isomerism. Coordination position isomerism. Now we'll see this complex. In this, here these two cobalt are there and the bridging is hydroxyl group, 4 amine molecules, 2 ammonia molecules and 2 chlorides. Now the coordination position is changing. One ammonia gets exchanged to this one and one chloride goes here. Okay, isomerism, it is shown only in the bridged. It is arised. So the isomerism, it is shown by the bridged complexes. It is arised due to difference in the attachment of the ligands, difference in the attachment of the ligands to the central metal atom. Here you can see 4 ammonias and here you can see 2 plus 2 chlorides. And in the next complex, 1 ammonia is getting exchanged here. Okay, 1 chloride is again exchanged here. So 3 ammonia molecules, 1 chloride and the 1 chloride molecules. Okay, within the sphere, the ligands are getting exchanged. Previously, you have observed within the here, previous slide, what we have seen here, coordination. Here, the ligand is completely getting exchanged here within the coordination sphere. Here, the central metal atom is changing the coordination sphere. The central metal atom is changing the coordination sphere. That is coordination isomerism. And in this one, they are not changing within here. Their ligand is changing within the sphere. There the central metal atom is changing between the coordination spheres. Whereas here, the ligands are getting exchanged within the coordination sphere. Okay, so previously you have observed now, here the central metal ion is changing from coordination sphere to the coordination sphere. Here the ligand is exchanging within the sphere. Okay, formula is the same, but here 4 amines, 2 amines, 2 chlorides. Now 1 amine ammonia molecule exchanged here and 1 chloride has got exchanged. Okay, this is coordination position isomerism. Now we'll go for the last one in the structural isomerism, that is the polymerization isomerism. In the polymerization isomerism, they are having same formula but differ in the molecular weight. Okay, so almost it's the same, the complexes. The complexes which have the formulas will be having the formulas almost the same. Here you can see the platinum complexes, but they differ. They differ in the molecular weight. Okay, so the molecular weight is getting exchanged. Such type of isomers are called as a polymerization isomerism. So they change in their weight. Okay, such type of isomers are called as the polymerization isomers. Now Here you can see platinum, ammonium chloride. Here diamine, dichloroplatinum complex, tetramine, platinum complex, and the tetrachloroplatinum complex. Similarly, triamine, trinitrocobalt complex, hexamine. Here, the hexamine, the molecular weight is changing. Molecular weight is changing for us. Okay, so now let us go for the next isomerism. Then the next one is the stereoisomerism. So structural isomerism, we have seen the structural isomerism. We have seen 6 types of isomerisms. That is nothing but one is the ionization isomerism, hydration isomerism, linkage isomerism, coordination position isomerism, and polymerization isomerism. Now let us go for the next one. That is a let us go for the next one. It is a stereoisomerism, second type of isomerism in the complex compounds. The second type of the isomerism in the complex compounds. That is nothing but here a stereoisomerism. What is stereo? What do you understand by the name stereo? So stereo, it is nothing but the spatial arrangement, the compounds having the same formula but differ in the spatial arrangement, the three-dimensional arrangement of the atoms and the groups or the molecules is called as a stereoisomerism. So this stereoisomerism, it is again of two types. One is the geometrical isomerism and the other one is the optical isomerism. So we'll see the geometrical isomerism. So geometrical isomers, I'm repeating, stereoisomers, the compounds having same formula but differ in the spatial arrangement of the groups and atoms is known as stereoisomerism. Stereoisomerism is of two types, geometrical isomerism, optical isomerism. So geometrical isomerism, isomers having same formula but the ligand's occupying position is different. Such type of isomers are called as the geometrical isomers. Isomers with same formula, but ligand's occupying position is different. Okay, again these geometrical isomers are of two types. Okay, so if the identical ligands are on the same side, if the two identical ligands are on the same side, then you call it as a cis isomer. If the two identical ligands are on the opposite side, okay, opposite to each other in the sphere, then that is a trans ligand. This geometrical isomerism you can observe in the square planar complex. Square planar complex you can observe, not in the tetrahedron. Here the square planar complex is nothing but here ML4 type of complex is called square complex. You are having even the tetrahedral, their sp3 hybridization, dsp2 is nothing but square planar complexes. You know. So the coordination number is 4. If it is ML6, so that is the coordination, ligands are 6 and the coordination number is 6. There if they exhibit any isomerism, that is the octahedral complexes isomerism. Now in detail we'll see square planar complexes. So according to the formula, how the different types of square planar complex isomerism is exhibited. Now, so geometrical isomerism for the coordination complexes with coordination number 4. Here you can see Ma2B2. A, B are the ligands. A is one type of ligand, B is one type of ligand. These both are monodentate ligands. The dentation site is 1. So monodentate ligands. In these ligands, here I'm giving you an example. Here, diamine dichloroplatinum complex. This is one complex. Diamine dibromo complex. This is the second one. And the third one is you are having different examples are there. Diamine dinitroplatinum complex. I have taken one example here and I explaining you cis type and trans type. Geometrical isomerism for square planar complexes. Coordination number is 4 and one type, that is A2B2 type, we'll see. So two same ligands. Okay, so for that examples I've taken 3 examples. In these 3 examples I'm explaining one example. So this complex is having cis as well as trans. Even this will have cis and trans. Even the third one will have cis and trans. So for diamine, dichloro, platinum complex, the two chlorides are on the adjacent side, same side, and the two ammonia groups are on the same side, adjacent side, side by side. Okay, that is cis complex. And here the ammonias are on the opposite side for the central metal atom, and they're opposite to each other. Here the chloride groups are opposite to each other. Okay, so that is a trans isomer. For Ma2B2 type of complex, it is trans type. Now the other type I'm explaining you, that is ABCD type. MABCD, four ligands, different ligands, but monodentate ligands. ABCD are four ligands, ML4 type only, but all the L's are different. Okay, now I have taken here an example. So that example you can see here. One is the ammonia ligand. Okay, one is a pyridine ligand. One is a chloride ligand and the bromide ligand. Okay, so according to the alphabetical order, you can give bromo here, amino, bromo, chloro, pyridine, platinum complex. So it exists in three different forms. In the similar way, you can write even for these two complexes. But now I have given you the geometrical cis trans type of examples here. Three forms here: ammonia and the bromide, pyridine and the chloride. These exist in the different types. Okay, and again ammonia, chloride, pyridine, bromide. For different ways they exist. Even this is a geometrical isomerism. You can't see here any cis and trans, but they're all different directions. Here ammonia direction opposite to this bromide direction. Here ammonia direction opposite to this you get the chloride, and here ammonia direction opposite this you are having the pyridine ligand. Okay, so different forms you are able to see. So here the main this strongly for this main ligand, ammonia ligand, the three ligands are in three different positions. So to the ammonia you are getting, once you are getting the bromide, next you are getting the chloride in the opposite side, in the pyridine. So here no cis and trans given. This is a type of geometrical isomerism for MABCD type. This is a type of geometrical isomerism for square planar complexes of MABCD type of complex. Now we'll go to the another type of square planar complexes, that is Ma2BC. Two ligands are same and two ligands are different. All of them are the monodentate ligands. These will show the cis-trans isomerism. Okay, so here you're having bromo, dichloro, iodo, palladium, anionic complex. We'll see here the two chlorines on the same side, so it is cis. The two chlorines on the opposite side, you get the trans. Okay, so this is a type of, here also you can see. Okay, so Ma2B2 you can see cis and trans. Ma2BC you can see the trans, but MABCD you can see the geometrical isomerism, different ways of arrangement, but not cis and trans. Now let us go for the next one. MAB pole of twice type of complex. This is unsymmetrical bidentate ligand. A and B, two different coordinating donor atoms will be there, and thereby you'll be getting the cis trans. The coordinating sites will be different. Okay, the coordination sites are different. By that you'll be getting the cis trans isomerism. Okay, glycinato ligand we are taking. Here is the structure. Glycinato ligand, GLY twice, platinum complex. One side you're having the nitrogen and oxygen donor atoms. Okay, so once if you clearly observe, here is the platinum complex, NH2, CH2, C double bond O, bond O. Again here NH2, CH2, C double bond O. Here the dentation site is O and here also it is O. Therefore it is cis. Same side the donor atoms. Okay, oxygen is being attached. So oxygen is a donor atom to the central metal atom. Here also oxygen is a donor atom to the central metal atom. Therefore, you are getting the cis type of isomerism. Here you can see even this is a cis. One side nitrogen, the same side even the nitrogen is the donor side, and the other side oxygen, and the other side is oxygen. Even this is cis. Donor, same type of donor atoms on same side. Okay, this is cis type of isomerism for AB whole of twice type of complex. Okay. Next, the other one is platinum complex. Here the donation sites are on the opposite side. One is the oxygen donor atom. Here also the oxygen is the donor atom, or both of them are on the opposite sides. This is a trans type to the center here. Oxygen opposite to oxygen. Okay, central metal atom. Or amine and amine group here, opposite side. Okay, and similar way here also the nitrogen is the dentation side, opposite you're having the nitrogen, oxygen and oxygen. Okay, so in this way you are getting the geometrical isomerism for bidentate, unsymmetrical bidentate ligands also we can see. Now we'll see in the square planar complexes, 4 types of complexes I've explained. Now we'll see the octahedral complexes. The coordination number is 6, Ma6. Okay, so Ma6 type of complex is there. MAAA whole of 3 complex is there. See, A's are 3, again A's are 3, total 6. Again A5 B type of complex also you can observe. Okay, now these do not show generally. These a single isomers we can see for this. These are all the coordination complexes. You can see the single isomers. They do not show the geometrical isomers. So MA4, previously in the square planar complexes M, A, B, C, D, you can see the isomerism, but cis and trans we can't observe. Now we'll go for MA4 B2 complexes. A, B are monodentate ligands. Okay, 4 are A and B are 2. Here, tetramine, dichlorotetramine, cobalt complex. We'll see. Cis and trans we can observe this code. So chloride on the same side. Okay, so remaining 4 are on the same side. Okay, these 2 are on the same side and these 2 on the same side. So therefore, this is a cis isomer, 1, 2 cis, 1, 2. And the next one is the trans isomer. In this trans isomer, you can observe the trans isomer. Chlorides are on the opposite side. Chlorides are on the opposite sides. So 1, 6 trans. Here 1, 2 cis. 1, 6 is trans isomer. Okay. A4 B2 type of complex, you are having cis and trans. A6, AA3, A5B are only single isomers. They are coordination number is 6 octahedral complexes, but they don't show the cis and trans isomers. Now we'll go for the next one, MA3 B3 type. Here you are having 3 of the AB are the monodentate ligands, and A3 and B3 ligands are there. Here is the example, tri-amino trichloro cobalt complex. They exist in cis. Okay, 1, 2, 3 cis. You can call 1, 2, 3 cis pack. Okay, 1, 2, 3 on same side, and 4, 5, 6 on the same side. Okay, and here you can see 1, 2, 6 on the here 1, 6 is in the opposite side. Here 3, 5 is in the opposite side. So this is a trans isomer. Here because these 2 chlorines are on the same side, you can take it as a cis. Here 1, 2 are on the same side, but here 3 is also in the same side. Here the 6 has gone to the opposite side. Once if a chlorine is opposite to chlorine, then that is trans. Any of the chlorine opposite to the chlorine is a trans. Any of the, here not only chlorine, it can be even the amine groups. Here amine is opposite to amine, chlorine is opposite to chlorine. Okay, here amine is this ammonia ligand on the same side, chloride same side, or else chloride and this chloride 1, 2, these are also same side. So 1, 2, 3 all on the same side. 4, 5, 5, 4, 6 on the same side. Here also you can see 1 and 2 on the same, but 6 is going to the opposite. So one chlorine is opposite to the other chlorine. One ammonia is opposite to the other ammonia molecule. So this is a trans. Just remember, for this type of ligands, here, same type of groups on the same side. Here, same type of groups on the opposite side. Any two enough. That goes for the trans. Now, the third type of the complexes we'll see. The third type of the complexes in the octahedral Ma2BC. Two ligands are same and two ligands are different. Here, these show cis-trans isomerism because two ligands are same type. If all the six are different, then you can't show. Okay, so this this is an example for the square planar complex Na2BC. Okay, dichloro, here total number of 4 ligands, square planar complex. Actually, this is a square planar complex. Okay, so for the square planar complex, we are seeing the cis-trans isomerism. Okay, octahedral completed, previous slide. Now this is the cis-trans isomerism for the square planar complex of Ma2BC complex. Now, two same type of ligands. They show cis-trans isomerism. Palladium, dichloro, bromo, iodo, anionic complex. Okay, bromo, dichloro, iodo, palladium complex. If a type of ligands, that can be anything. Here it is chlorides on the same side, so it is cis. Chlorides on the opposite side, that is trans. Okay, so this already explained, the same example is repeated. Okay, we'll see optical isomerism. Optical isomerism. In the optical isomerism, in the stereoisomers, geometrical isomerism is completed, and now in the stereoisomerism, the second category is optical isomerism. So compounds having same molecular formula, physical, chemical properties are same. Physical and the chemical properties are also same, but differ in rotating the plane polarized light. What do you mean by PPL? Plane polarized light. Monochromatic light. The light in single direction is PPL. Plane polarized light is called plane polarized light, monochromatic light, which is in the single direction. Okay, so here optical isomerism. They differ in the rotation of the monochromatic light, plane polarized light. Such type of compounds are called as the optical isomers. Compounds with same formula, chemical and physical properties, differ in rotating the PPL are known as the optical isomers, and the phenomenon is called optical isomerism. This optical isomerism is shown in the complexes having coordination number 4, that is tetrahedral complex. Geometrical, we are able to observe in the square planar complexes, coordination number 4. And for coordination number 4, optical is observed for tetrahedral complexes. In the stereoisomerism, coordination number 4, geometrical observed in the square planar complexes, optical isomerism is observed in the tetrahedral complexes. And the same optical isomerism is observed even in the octahedral complexes. So octahedral, it is having both the geometrical and it is having the optical. For the coordination number 4, square planar is having geometrical isomerism, and coordination number 4, tetrahedral, is having optical isomerism. Now we'll see in the tetrahedral complexes. So tetrahedral complexes, bis-benzyl acetonato-beryllium complex, we'll see. Bis-benzyl acetonato complex, we'll see. In this complex, you can see the structure. So the central metal atom, we are able to see the central metal atom, that is a beryllium. Okay, and you are having two bis, you call a complex ligand. So that is a benzyl acetonato complex. This is the benzyl group. This is acetonato group. Acetonato group, benzyl, okay, benzyl, okay, C6H5CH2, this is the benzyl group, and acetonato group attached to the beryllium central metal. How many are there? 2 are there. Okay, so you can see 2 groups. That is why I'm calling you as a bis. Why you are calling as a bis? Because there are 2 groups. This is a, here you can you call it as a bis because the complex it is a it's a complicated, it's a biggest ligand. Okay, so it's nothing but just like a chelate ligand. We use here bis group, bis word. So beryllium benzyl acetonate, beryllium benzyl acetonate complex. These are mirror images. What if you put them? The plane polarized light rotation is different. Okay, plane polarized light rotation is different. Once here, these are enantiomers, these are the, here you can see the mirror images. Okay, so one will rotate the light in the right side direction. One complex will rotate the plane polarized light in the right side direction, and the other one will rotate the plane polarized light in the left side direction. Okay, so that such type of complexes are called as the optical isomers. Once if they rotate the plane polarized light in the opposite side, then they're called as the optical isomers. They're called as the optical isomers. One will rotate in the right direction, one will rotate in the left direction. Okay, for tetrahedral, this is one of the example. Okay, 4, the coordinating sites, 4 tetrahedral complex. Now we'll see the optical isomerism in octahedral complexes. For 2 types of formulas, you can observe this octahedral complex. MAA2B2, total 2 to 4 plus 2, 6. 6 ligands, AA twice B2. So ethylene diamine complex, and this is ethylene diamine dichlorocobalt complex. This is one type of ligand and this is other type of ligand. Okay, so that ethylene diamine, okay, that ethylene diamine, the coordinating sites, the ligands, they are the complex ligands. Okay, so here cobalt complex is there, ethylene diamine you're having how many? 2 ethylene diamine and 2 chlorine atoms. Here chlorine ligands. This is 2 ligands and these are 2 ligands. Okay, polydentate ligands. Ethylene diamine complex, 2 dentation sites, bidentate ligand, 2 dentation sites. Here also 2 dentation sites. Ethylene diamine. And here you're having, this is monodentate ligands, 2 chlorides attached to the cobalt. Okay, so here bidentation, total 4. Here unidentate ligands 2. Therefore, monodentate ligands 2. Total 6 is the coordination number. 6. Here you are having 6 bonding sites. Here dentation is 6 here for the central cobalt metal atom. Now, once if you see, this is the mirror image. It is quite opposite. Quite opposite you can see. Okay, so previous complex you are having almost the same type of groups. That is why we are not able to see clearly for this complex. Almost same groups we are able to observe, and therefore, but the rotation is different, but we are able to not identify in the picture. Okay, so here for the octahedral complexes, coordination number 6, AA twice, whole twice, B2 type. Here diamine dichlorocobalt complex. Here also diamine dichlorocomplex. This is opposite to this one, and this is opposite to this one. Chlorides are almost opposite. These are just like the mirror images. This will rotate in the right side. Plane polarized light is rotated in the right side. Okay, D form. This is the L form. The plane polarized light is rotated in the left side direction, anti-clockwise direction. So it is rotated in the clockwise direction. It is rotated in the plane polarized light is rotated in the right side by this complex. Here the plane polarized light is rotated in the left side. See, you can see the arrow. It is rotated towards the left side, anti-clockwise direction. So this is D form and this is L form. Okay. So now the other type of complex for the octahedral complex, AA3 type. AA3 is nothing but tris ethylene diamine cobalt cationic complex you take here. Okay. This is opposite to this group, and this is opposite to this group, and this is opposite to this group. Here the plane polarized light is rotated in the clockwise, you can see clockwise direction, that is D form. Here the plane polarized light is rotated in the left side, that is anti-clockwise. Anti-clockwise, it's anti-clockwise. Here it is clockwise D form dextro-rotatory. Here anti-clockwise left side levo-rotatory. Okay, so this is about the isomerism. So once again, just I'm recalling what I have explained. So isomers in the complexes. First one is the structural isomerism. Structural, you're having 6 types. You're having ionization, aqua, linkage, coordination position, and polymerization isomerism. And coming to the stereoisomerism, you are having geometrical and optical. Geometrical, you are having cis-trans. We have seen for the square planar complexes, different types of formulas. Octahedral complexes, different types of formulas. And optical isomers, you are having for the tetrahedral complexes, I have shown you. And for the octahedral complex of different formulas, we have seen optical isomer. Okay, stereo, we have seen geometrical and optical isomerism. I hope everybody have understood my class. Okay, so thank you everyone.